Hello friends, in this video I'd like to solve the following problem from the Brazilian Mathematical Olympiad, final round, year 2010, problem number 1. We want to find all functions f from the set of real numbers into itself, such that f of x times y equals f of x plus y for all irrational numbers x and y. So function is given on the whole field of real numbers, but this functional equation need to be satisfied only for irrational numbers. So my hints for this problem: first of all, it may be a good idea setting the following: y equals 1 over k times x, where x is irrational and k is any positive integer, and then to consider the range of function which takes non-zero real number x and outputs x plus 1 over k times x. And finally, notice that if x plus 1 over k times x is irrational, then x must be irrational as well. So give this problem a try and I will see you in a minute. Okay, so I hope that you've managed to solve it. So first of all, set k to be any positive integer, and so let k be positive integer, let x be any irrational number, and let y be equal 1 over k times x. Well, it means obviously that y is irrational as well. Y is irrational as well, and plugging into our equation, we see the following: x times y equals 1 over kx, 1 over k, sorry, and on the right hand side we have f of x plus 1 over k times x. Very well. And now let's consider this function right here. And now let's say g of x be equal to x plus 1 over k times x for any non-zero number. Let's find the range of this function. How can we find the range of this function? Well, either by the methods of mathematical analysis or by some kind of estimation. Maybe I will avoid using derivatives. You can differentiate this and find the maximum and minimum and so on. I will do something slightly different. First of all, notice that if x is positive, then we can write g in the following manner: square root of x squared plus 1 over square root of k times x squared minus 2 over square root of k plus 2 over the square root of k. And that is square root of x minus 1 over square root of k times x, quantity squared, plus 2 over that. Okay, and now it should be visible that the minimum of our function, since this number is clearly non-negative, the minimum over positive numbers of our function g of x, it's 2 over square root of k, and moreover it should be visible that limit as x goes to infinity of g of x is plus infinity, and that means, by the continuity of our function, that means that the range, and moreover, let's also notice one more thing: function g is odd. it's visible that we have only odd powers of x, so g is odd, and these three facts imply that the range, the image of our function is minus infinity minus 2 over square root of k union 2 over the square root of k. Let's move it a little bit. Sum plus infinity. Okay, very nice. And now let's do the following. Let's take now let for example z be any irrational number from this sum of intervals. So we take number from this set and also irrational. Then we know that z equals g of x for some a real number x, and moreover this x is also irrational. Why? Because let's look once again at the formula for function g. If x is rational, then g of x is also rational. So if g of x should be irrational, then x should be irrational as well. Okay. And that means that let's go back. F of 1 over k equals f of z. Okay. And remember that that's true. I will put quantifiers. That's true for every positive integer k and for every irrational number z from our sum of intervals. Okay. So that means, in other words, that means that our function f is constant on every set of this kind. So f is constant on irrational numbers intersected with every interval of this kind. And these intervals, if you think about them, they are getting closer and closer to 0. This end gets closer to 0 from the left hand side, and this end also gets closer and closer to 0. They form so-called descending chain of sets, ascending chain of sets. And in the limit, as k becomes larger and larger, taking k going to infinity, we deduce that f is constant on the whole set of irrational numbers. Because 0 is irrational, so 0 doesn't matter. Okay, so now we know something. We know that our function is constant on the set of irrational numbers. Well, but what's about rational numbers? Let's see. So let's take our equation once again. It was f of x times y equals f of x plus y for irrational x and y. And now let's do the following. So let, for example, a be a rational number, rational this time. Then rational, and let's say not 0. Then what can we do? Oh no, let's take any rational number. Set x equals the square root of 2 and y, let's set y to the a minus the square root of 2. It's clearly visible that both of these numbers are irrational, and that means that f of square root of 2 times a minus the square root of 2 equals f of a. Okay, but that means that f a times square root of 2 minus 2 equals f of a, and that means that if a is non-zero, then a square root of 2 is irrational, and that implies in turn that f of a equals f of some irrational number, and that means that f of a is this one constant value, which is attained by every irrational argument. So f is constant on the set of every number with, but we don't know about 0 for now, because that argument works only for a which is non-zero. And finally, let's check the value, what happens at 0. Well, at 0, so at 0, what happens? We can finally set x equals, let's think about it. Let's set, oh yes, square root of 2, y let's equal minus square root of 2. Then f of square root of 2 times minus the square root of 2 equals f of square root of 2 minus square root of 2. So we have f of minus 2 equals f of 0. So now we know that value of f of 0 is the same as the value of f of minus 2. So we now know that our function f is constant on the whole set of real numbers. F is constant on the entire R. Okay, so only constant functions can satisfy our functional equation, and it's pretty easy to see that every constant function satisfies our equation, because on the both sides we have the same constant. So finally, solutions. Our equation satisfied if and only if f is constant. And that closes our solution. So let's go once more through our reasoning. So first of all, I have considered positive integers k, and I set specifically this argument y. Then I have investigated the range of this function. I have established that the range of this function is this kind of this sum of intervals, union of intervals. And then I have noticed that in fact I can take any rational number from this set, And this value is attained when the argument on function g is also irrational. And that meant that f of 1 over k equals f of z. And since k was chosen as any positive integer, I took k to infinity, limiting case, and I have noticed that my function is constant on the whole set of irrational numbers, because these boundaries are getting closer and closer to zero. Every non-zero number will be in this sum of intervals for sufficiently large k. So by now I know that my function is constant on the set of irrational numbers, and now I just need to verify what happens on the set of rational numbers. So I take any rational number a, I set these two specifically chosen numbers, which are obviously irrational. I saw that it's satisfied, this equation is satisfied. On the left hand side I have f of some rational number. On the right hand side I have f of some rational number. On the left hand side, if a is non-zero, I have f of some irrational number. And remember that this is a constant, so f of a is also equal to this constant value, which means that my function f is constant on the whole set of real numbers, but not necessarily for 0. And finally, by taking a equals 0, by taking x equals square root of 2 and y equals minus square root of 2, I see that f of minus 2 equals f of 0, which means that f of 0 is the same constant value, which implies that our function is constant on the whole field of real numbers. Okay, so I hope that you learned something new. I hope that you've enjoyed my video, my talking. And yes, see you next time. Goodbye.